This slideshow is all about earthquake magnitude. The magnitude of an earthquake is a measure of its size, or the amount of energy it produces. Earthquakes with big magnitudes produce severe shaking that is felt a long way away from the epicenter, while earthquakes with small magnitudes are only felt weakly and locally. Probably the most familiar magnitude scale is the Richter scale, which was invented by a seismologist named Charles Richter in 1935. As we'll see, the Richter scale is a rather crude measure of earthquake strength, but it's easy to use and works pretty well most of the time. Today, seismologists use a more sophisticated and accurate magnitude scale called the moment magnitude scale, but for small to moderate sized earthquakes, the two scales give about the same value. Richter magnitude is measured from the seismogram, or record of ground shaking, like is shown here. This is a typical seismogram produced by some distant earthquake. You can see the arrival of the P wave on the left, and then later, by about 20 seconds, the arrival of the S wave. The surface waves will presumably come in sometime later and aren't shown here. The Richter magnitude is based on the largest amplitude of shaking, regardless of the kind of wave. For example, in this case, it's the S wave, which has an amplitude of about 23 millimeters. So the magnitude of the earthquake will be based on that measurement, 23 millimeters. Stronger earthquakes would have produced a larger amplitude of shaking, and smaller earthquakes would have produced less. Of course, the absolute amount of shaking depends both on the strength of the earthquake and how far away it was. Nearby earthquakes might produce a lot of shaking even if they're small, and a giant earthquake might only produce a tiny amplitude if it occurred on the other side of the Earth. So the amplitude needs to be corrected for distance because of attenuation, which you might remember is the decrease in amplitude of a wave as it travels away from its source. You can see how the amplitude of this surface wave in the animation here in blue decreases as the wave moves from left to right. And if you look at the four different seismograms I've shown below that, recorded at greater and greater distances from the epicenter, you can see that the amplitude of all the waves decreases as you get farther away. So the Richter scale has to account for this fact when it makes the conversion between the amplitude and the magnitude. To calculate the Richter magnitude, then, you take the amplitude of the largest wave seen on a seismogram and make a correction for distance to the epicenter. All magnitude scales, including the Richter scale, are logarithmic scales. The log is nothing more than an exponent. It's the exponent needed to produce a number given a specified base number. For amplitude, the base number is 10, which produces the most common logarithmic scale. So if 1,000 can be written as 10 to the third power, then the logarithm of 1,000 is 3. It's the exponent needed on 10 to make 1,000. You can define logarithms for all numbers, even ones that aren't simple, like 100 or 1,000. For example, the logarithm of 250 is 2.3974 with some more numbers, which means that 10 to the 2.3974 blah 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 is equal to 250. Also note that logarithms can be negative, since negative exponents are defined. So 10 to the minus 2 is defined as 1 over 10 to the second power, or 1/100th. So the logarithm of 1/100th is negative 2. Logarithmic scales are useful when a set of numbers has an enormous range. For example, suppose we wanted to describe something that ranged from 1/10,000th to 10,000. We'd need at least 8 digits to describe every number in that range. If we use the logs of the numbers instead, we'd only have to use the numbers between -4 and 4. The thing to remember when using a logarithmic scale is that the actual number, not its log, doesn't increase linearly. So when we go up one log unit, the actual number increases by a factor of 10. When we go up 2 log units, the number goes up by a factor of 10 times 10, or 100. This is how the magnitude scale works with the amplitude of shaking. Here's an example. Suppose you had an earthquake with a Richter magnitude of 3 that produced 2 centimeters of shaking on a seismogram. How much more shaking would be produced from an earthquake with a Richter magnitude of 4? By the way, the symbol for the Richter magnitude is M sub L, where the L stands for local. The answer is 20 centimeters of shaking, 10 times more than 2. Remember, when the magnitude increases by 1 unit, then the amplitude of shaking increases by 10 times. Here's another example shown in orange. Suppose an earthquake of magnitude 3.7 produced 10 microns of amplitude on a seismogram. How much would the needle move if the magnitude had been 1.7 instead of 3.7? The answer is 100 times less, or 0.1 microns of amplitude. Here we've decreased the magnitude by 2 units, so we have to decrease the amplitude by 10 times 10, or 100. So it has to be 1/100th as big as it was before. Hopefully you can see from these examples why magnitude scales are logarithmic. The range of shaking amplitudes produced by earthquakes is enormous, and by using a logarithmic scale we can compact a description of that range into about the numbers 1 through 9. The very largest earthquakes have a magnitude of about 9, maybe a little bit more, while the tiniest earthquakes have magnitudes that are actually negative. Remember that the magnitude of a logarithm can be negative. But in practical sense, the smallest earthquakes we're interested in have a magnitude of 2 or so. So we can describe all interesting earthquakes with a magnitude scale that ranges between about 2 and a little more than 9. Now there's one more aspect of magnitude that's logarithmic. That's the energy released by the earthquake. This isn't the same thing as the amplitude of shaking, which is just how much the needle jumps around on the seismogram. The energy released is actually a lot more complicated than that, but it can be related to the magnitude by logarithms of base 32. This means that each increment on the magnitude scale has a difference in energy released of 32. For example, let's do the same test we did before with amplitude, but this time with energy. How much more energy will be released from an earthquake of magnitude 5 compared to one of magnitude 4? The energy released is shown on the bar graph. The answer is that increasing one increment of magnitude implies an increase of 32 times more energy. That's a whole lot more energy. How about if we were to increase 2 magnitude units? For example, how much more energy would an earthquake of magnitude 6.5 produce compared to an earthquake of magnitude 4.5? The reason I don't show a bar graph here is because the bar graph for magnitude 6.5 would extend way past the top of the slide. This earthquake would contain 32 times 32, or about 1,000 times more energy than a magnitude 4.5. In fact, this is a good way to remember the relationship between energy and magnitude. The energy released increases by about 1,000 for every 2 increments in magnitude.